Everyone. So today we'll learn very interesting topic of solid state chemistry, or actually we can say the semiconductor chemistry, that is Fermi level and its variation according to its the doping and its the temperature. Okay, means how the Fermi level or the Fermi energy is changes according to the temperature, and it depends of temperature and how if we increase the temperature, or if we increase or decrease the temperature, and what is the result of that energy. Or we also learn about the doping, and if we increase if we dope another metals or in a semiconductor material. So the how the Fermi level energy changes we'll learn in this video. We'll cover everything in this video. Okay, so we'll start with Fermi level. Okay, Fermi level. So this term is very popular in semiconductor chemistry. Okay, so what is Fermi level? Fermi level can be defined in many ways. So we'll start with this one. So Fermi level can be defined as the highest energy level, that can be achieved by an electron at absolute zero temperature or 0 Kelvin temperature, that can be achieved by an electron at absolute zero temperature. Okay, that is actually 0 Kelvin temperature. Okay, so in absolute zero temperature, when the electron that can achieve the highest energy level, that is called the Fermi level. Okay, actually the Fermi level is that energy which has a 50% probability of occupation of an electron at absolute zero Kelvin. It can be defined as this well, means when means at this level, electron has 50% probability 50% probability. Okay, not 100%, it's a 50% probability of occupation. Okay, at 0 Kelvin temperature. Okay, that is also the absolute zero temperature, that can be defined as this also. Or we can define the Fermi level, that it may also be defined as the energy level that corresponds to the center of gravity of the conductance band electron and the holes present in valence band when they are weighted according to their energy. Means what I want to say, that okay, it may be defined as the energy level that corresponds to center of gravity of electrons in CV or conductance band. I am writing this as a CV short form, and holes in valence band or VV when means when they are weighted according to their energy. Okay, so what I am going to say, that means this energy, this Fermi level energy is like a balance of two energy levels. Means if I want to say, if this is a conductance band and there is a valence band, okay, so the number of the what it is defined as the energy level, this corresponds to the center of gravity. Okay, just focus on this term, center of gravity of electrons in CV, electrons in conductance band and holes in valence band when they are weighted according to their energy. Means I am to say that when the electrons, if one electron is excited to this conductance band, so there will be a hole that will occupy the place of that electron. Means I want to say the hole is created when one electron will excited to that conductance band. Okay, so number of holes present in VV is 1 and number of electron present in CV is 1. So if their energy will be same, because the energy of a hole is equal to the energy of a electron, because the one is positive is considered as a positive, hole is considered as a positive energy, and electrons is considered as a negative energy, but the energy value is same. Okay, so if the number of electrons in CV is equal to the number of holes in VV, then it will actually, the Fermi level will actually lie on the gap, on this gap is energy gap. Oh, okay, this gap is called energy gap. Okay, it's just at the middle of that energy gap. Okay, okay, so this is the Fermi level. So we'll learn about intrinsic semiconductor, intrinsic semiconductor. Okay, semiconductor, what is intrinsic semiconductor? So intrinsic semiconductor means pure semiconductor, means if there is no doping, only one type of metal is present in that semiconductor, then it is called intrinsic semiconductor. Okay, that means like a whole semiconductor is created or produced with silicon or germanium, that is 4 valency. Okay, so that one is called the pure semiconductor or intrinsic semiconductor. Okay, for intrinsic semiconductor, so this is a electron conductance band or CV. If this is a valence band or VV, this is the energy profile, the VV energy, and this is the top of that of valence band electron of valence band is called that EV. Okay, and the bottom of the CV or conductance band is the energy is called, that is EC. Okay, so the energy gap between this EC and EV is called in forbidden energy gap, that is EG. Okay, so for intrinsic semiconductor, our Fermi level will lie on the middle of the energy gap, that is EF. Okay, so EF equal to EG by 2. Okay, for intrinsic semiconductor. Okay, this energy level EF here is called also EI. So EI is intrinsic energy level. Intrinsic energy level. Intrinsic energy level. Energy level. Okay. EF is equal to here Eg by 2. Okay. Why this is? Because in intrinsic semiconductor, so the number of holes present in valence band is equal to number of electron present in conductance band. Okay. This is same. Why I am saying this is same? Because if consider that there is no electrons in present in CV at some temperature. Okay, so now I am increasing the temperature. So what will happen? The from this EV energy level, or this is valence band. From valence band, electron will absorb the energy and it will go the conductance in band. So number of electrons will go for conductance band. For that there will create the number of holes. So I am saying that a number of holes will produce in place of that electrons. The number of electrons will go to the conductance band. So number of holes present in valence band will always will same in number of electrons in CV. So our energy means, if we what is the Fermi level? Fermi level is defined as the energy level corresponds to the center of gravity when weighted there according to their energy. Okay, means number of, if the number is same in valence band and the holes in valence band and electrons in CV, so then the EF will occupy at will lie on the half of or middle of the energy gap. Okay, so this is intrinsic semiconductor. So now that is extrinsic semiconductor. Okay, what is extrinsic semiconductor? Extrinsic semiconductor. What is extrinsic semiconductor? Extrinsic semiconductor is impure semiconductor. Impure. Why I am saying, if this pure semiconductor is doped with some pentavalent elements or some trivalent elements, then it will be impure. It's not a pure semiconductor. So then it will create an extrinsic semiconductor. Okay, extrinsic means will put some, we dope some external metals to the semiconductor. Okay, so now we'll see the we are doing doping here. So it will affect that energy Fermi level significantly. So how this effect is conduct? So if so these two type. Okay, this is two type. Extrinsic semiconductor is two type. So one is n type semiconductor. Okay, that is when pure semiconductor or intrinsic semiconductor doped with pentavalent element, doped with pentavalent element. Okay, and p type semiconductor. P type semiconductor. Okay, that is doped with trivalent element, because our semiconductors are 4 with valency. The element is with valency 4, trivalent element. Okay, that is P type semiconductor. So now we'll read the start with N type semiconductor. Okay, semiconductor. Okay, when you introduce a pentavalent impurity, so it will introduce a donor energy level in this energy profile. Okay, so this is energy, this is our conductance band. Okay, and CB. Okay, CB. Okay, this is our valence band. Okay, so in the middle of CV and VB, that is EI. EI means intrinsic energy level. Okay, now this is E donor and that is EF. Okay, now we'll explain everything how this is happening. Okay, so when you introduce this pentavalent element in the semiconductor, it will introduce or it will create a new energy level that is called ED or donor level. Donor of what? That is electron. Donor of electron. Donor of electrons. Why it is create this donor of means electron? Because we doped with pentavalent element. Pentavalent element means the semiconductor is of, we are assuming the semiconductor is of silicon. Okay, silicon have 4 valency. Okay, but this is a pentavalent element, means there is extra one electron is present that is not bound with any other electron. So it is a free electron. It is all a free electron. So our main carrier in N type semiconductor is electron. Okay, there is one free electrons of each pentavalent element or each pentavalent center. Okay, so that electrons creates that donor level. It's not donor electron, that is donor level. Okay, donor energy level. So what it will do? Okay, so this energy level, from this energy level, electrons will go to conductance band. Okay, so what will happen? The number of electrons in conductance band will increase, but the number of holes in valence band will not increase that much, because we also from valence band also electrons will go to CV, means conductance band, but number of electrons present in CV is greater than the number of holes present in VB, because the many electrons come from this energy level is ED or donor energy level. So always probability of finding electrons in CB is greater than probability of finding holes in VV for this n-type semiconductor. So as our as the number of electron density, the electrons number of electrons is increasing, is greater than the number of holes in present in valence band. So the Fermi level also increase, because the energy of Cb is greater than, if we tell about the energy, if we talk about energy, so the energy will also increase for Cb. So what is Cb is the center of gravity of electrons present in Cb and holes in Vv when they are weighted according to their energy. So now the energy is increased here in conductance band. So the center of gravity will shift to upper side and it will lie in between that Cb and means conductance band and the donor energy level. Okay, understand? So why this energy level lie in between this conductance band and the donor energy level? This is the reason, because there is this energy level, from this Ed energy level, donor energy level, many electrons will come to this conductance band, and for this reason the number of electrons present in Cv is always greater than the number of holes present in Vv. So Fermi level also shift as the center of gravity shift to the this conductance band. So our Fermi level present in between this one, okay, in between this one. Now we'll check the p-type semiconductor. So for intrinsic semiconductor, Fermi level will lie at the middle of the band gap energy, but here is it will create a donor energy level n-type semiconductor, and our Fermi level will lie in between the Cb conductance band and donor energy level. Okay, we understand the reason behind this. So now this is a p-type semiconductor. Okay, p-type semiconductor. What is the p-type semiconductor? And when it is doped, our semiconductor is doped with trivalent element, means our semiconductor is, if it is silicon, if it is of silicon and it is doped with, like I am assuming that is a boron, doped with boron, so there one valence if this is silicon. Okay, so if so one electron is always unpaired for this silicon, means there is a hole will create, means if this is silicon, if this is silicon, if this is silicon, so for this okay, so only there is one hole present, one hole will create as the end at the center of B or at the center of trivalent element. Okay, and our main carrier in p-type semiconductor is hole. Okay, so we'll see the energy diagram. Okay, this is energy, this is our conductance band Cb, this is our valence band, so this is our in between this is our intrinsic energy. So for this, when a hole is created, so it will introduce a acceptor level, in between the EI and VV or EV, that is EV and that is EC. So our Fermi level lie in between this. Why? So hole is created here, okay. So this is an acceptor level, okay. So electron will accepted by this level. This is an acceptor level, okay. So electron will accept that by this level, okay. So what will happen? So number of electrons will go, so electrons will go from valence band to acceptor level as a result, and also it will go, the electrons will go to the conductance band as well, but the number of holes present in valence band will always greater than the number of electrons present in conductance band, because some of the electrons will go to the acceptor level, okay. So in this case, for this case, the probability of finding the electrons in CB or conductance band will always less than probability of finding the holes in valence band, okay. We'll remember this, okay. So our, if we talk about the energies, so if we consider the here the energies of our holes, and this is the energy of all electrons, so the energy of holes will always greater than the sum of the energy of holes will always greater than the energy of these electrons. So center of gravity will shift downward and it will lie between the acceptor level and this valence band energy level, okay. So understand why this Fermi level will go downside. This is our, in this case this is opposite to this one, okay. And here intrinsic semiconductor, probability of finding the electron in CV is equal to probability of finding the holes in VB, that is for intrinsic semiconductor, and this is for extrinsic semiconductor, okay. Now this is the variance of energy level or Fermi energy level with the doping. Now we'll see that variance of the dependence of temperature, okay. Dependency of temperature, okay. Dependency on temperature, okay, of Fermi level or Fermi energy. So for first we'll talk for intrinsic semiconductor, okay. Intrinsic semiconductor, or we can say intrinsic, okay, semiconductor. SC is called intrinsic semiconductor. So what will happen if we increase the temperature or decrease the temperature? This is our conductance band and this is our valence band, okay. So as a certain temperature, okay, when this is our EF, that is equal to EI. So for this case, if we increase the temperature, so what will happen? The electron will go from valence band, more number of electron will go from valence band to conductance band, nothing will happen. So as the number of electrons will go from valence band to conductance band, in their place their holes will created. So always at any temperature, if we decrease the temperature or if we increase the temperature, at any temperature, the number of electron, the number, if n is the number of electron in Cb, is always equal to number of holes in Vb. Nothing will change, because all electrons, if we increase the temperature, what will extra happen? Nothing will happen. So only happen just the electrons will go upside, and by absorbing the energy, and it will go for the conductance band, and in their place one hole will created. So just one electron will go and one hole is created in their place. So number of electrons is equal to, always equal to, number of holes will present in Vb. So there is no temperature, with temperature this energy level which never change, this will never change. Ef of intrinsic semiconductor will never change, will never change with temperature. Okay, so it will, if this is energy, so if we graph plot, if the energy and this is temperature, if we increase the temperature, it will constant in all the graph, or all at all temperature it will constant. Okay, this is our graph plot. Okay, now we'll talk about for the extrinsic semiconductor. Okay, extrinsic semiconductor. Extrinsic semiconductor. Okay, so what will happen for extrinsic semiconductor? EV. Okay, this is our conductance band and this is our valence band. This is for n type. Okay, n type semiconductor. Okay, this is our Vb or valence band. Okay, so now if it increase the temperature, what will happen? At this point, at any temperature, this will happen. Okay, the number of electrons present in Cb will always greater than the number of holes present in Vb. Now we'll increase the temperature. So if we increase the temperature from valence band, electron will excited, absorb the temperature, absorb the energy, and excited to the conductance band. Okay, so from this point, okay, from this point, if I am saying there is 3 electron, 1 2 3, if these 3 electron will absorb the energy and go to the conductance band, but when it increase the temperature, more number of electrons from valence band absorb the energy and will go for the Cv or conductance band. So what will happen? So number of, as we increase the temperature, gradually the number of electrons from valence band, number of electrons from valence band, okay, number of electrons from valence band also increase, means I want to say that gradually more number of electrons will come from valence band. So what will happen? So if more number of electrons come from the valence band electron, then the number of holes also increases. So number of holes also increases. So what will happen if number of holes increases? So according to the energies, so number of the energies or the weight energy or energies of holes also increases at valence band. So as the then center of gravity will shift it to downward. So this energy level will gradually, means this EF Fermi energy level will gradually goes downward. Okay, which gradually goes downward. Okay, just a minute. Which gradually go to the downward. Why? Because the number of holes also increase with if we increase the temperature gradually. Okay, so what will happen actually if we plot the graph? If this is energy, this is our temperature, if this is our EI, so and first this is our EF at certain temperature or zero temperature I am saying. So if we increase the temperature, it will come this way, means the energy level of Fermi level energy will come to the intrinsic energy level or middle of the energy gap, but it will not cross the intrinsic semiconductor and will not come beyond below the energy level. Why? Because at certain temperature, at any temperature, if whatever we increase the temperature, at any temperature the number of electrons will never, the number of electrons at CV will always greater than, will at any temperature, number of electrons in CV will always greater than the number of holes in valence band. Because why? Because at any temperature, so if we gradually increase the temperature, the number of electrons from VB or this valence band will go to the conductance band, but there is extra source of electron, that is ED. From ED also there is electrons will go. So number of electrons at any temperature is always greater than the number of holes in VV. So it will never touch, or we can say it will never cross that intrinsic semiconductor intrinsic energy level, and it will not come down or below that EI energy. So what will happen for the p-type semiconductor if we increase the temperature? Okay, this is our E. So this is conductance band and this is our valence band. Okay, this is our intrinsic energy level, this is our acceptor level, and this is our EF. So what will happen if we increase the temperature? What will happen? From here electron will go to the same. What will the same happened in for n-type semiconductor? The same thing will happen. The energy will absorbed by the electrons from at VB or valence band, and it will go to the conductance band. So what will happen? The number of electrons is gradually increase if the temperature is increases, gradually increase for the CV or that conductance band. But there is some electrons which go also for acceptor level at some temperature. Okay, and but the at this level there is, if there are three electrons will come from the VV, but if we increase the temperature, more number of electrons come to the CV. So if we increase the temperature, the number of electrons at conductance band will always also increases. So the center of gravity, so if we add that the energy, if we sum their energy, so then if we increase the temperature, with that the sum also the energy also some of the energies of electrons at present at conductors also increases. So center of gravity will shifted upward, means it will go upside this Fermi level energy. So now if we plot this one, if this E and this is our EF at temperature 0, I am saying EF, so this is our EI, so it will go this is our graph. This will come for n-type semiconductor, Fermi level will come downside with increase of temperature, and for p-type semiconductor with increase of temperature EF will increase and it will come just below the EI. It will never cross the EI, or it will not the energy will not above the EI EF, because that's at any temperature from like this, at any temperature number of holes present in VV is always greater than the number of electrons present in conductance band. Why? Because the sum of the electrons also go for the for that acceptor level. For that reason, number of holes always greater in valence band is always greater than the number of electrons in conductance band. So this is our theory and how this temperature. So at the summary, this is the temperature dependence. So for intrinsic semiconductor, it will never change the energy level of EF it will never change, but for a extrinsic semiconductor it will come downside. For for p-type semiconductor it will come upside. For n-type semiconductor it will come downside. Okay, now we'll do some question from in the it came in CSIR net exam, so it will give a better experience about this theory. Okay, so it came in June 2011. So what is the question? That consider a n-type semiconductor, okay, whose EV is 0, EC means its conductance band energy level is 2 EV, and ED is minus 1.98 electron volt. Okay, so it's not minus. Okay, just a minute, I am checking. Just a minute, I am checking the question. Just wait. so it is not minus, it is plus. Okay, so EC means our question EC, that is 2 electron volt, ED, that is 1.98 electron volt, and EV is 0 electron volt. Okay, so which will be the correct option? Okay, so first one is EF is 1 electron volt. So for this this n type electron volt, so there is a energy level of donor electron, energy level. So our EF will just lie in between the EC and ED, just so EF will be 2.0 plus 1.98 by 2, that is 1.99 electron volt. Okay, so first option is not correct, it's not correct. So second option, EF is 199 is okay, but it remains independent with temperature. We know that for n type semiconductor, especially for extrinsic semiconductor, the EF or Fermi level is not independent of temperature. For intrinsic semiconductor, it is independent of temperature, but for extrinsic semiconductor or n type semiconductor, it will not, it is dependent of temperature. EF is okay, but okay, this is correct option, but increase towards the 2 EV. It's saying that EF is increased to the EC 2 EV, and with increase with temperature. That is also not correct, but because we read that because the EF for n type semiconductor with increase of temperature, it will gradually come downward, and it will lie just above the EI, that is intrinsic energy level. So that option is all incorrect, and this EF is 1.9 decrease with temperature, so this is the correct option. Okay, this is very easy question. Our next question, that is came in June 2014, that when silicon is doped with group V element, means like for any group V element, so donor level are created close to the valence band. Donor level is means pentavalent is doping element is pentavalent, means n type semiconductor. Okay, so there a donor level will create, so it will create close to the conductance band, because we just read this one n type semiconductor, this is our donor level, that is close to the conductance band. So our correct option will be this one. So these two questions came from this topic in NET exam, CSIR NET exam. So we read this topic and understand these, how these questions and this level of questions came from this topic. And this is very easy, you just have to remind some concept from this level, and it will be very easy to do any such questions from that came from at any GATE or NET exam or any JAM exam. So I am ending this video here, and if you like this video, subscribe my channel and tap the bell icon if any video come in my channel, so that you can easily get that video in YouTube. So thank you, bye bye.